Hello, everyone. My name is Haokai Zhao. I'm a PhD student from Columbia University's Civil Engineering Department. Today, the project I'm going to present is a LoRaWAN-based environmental sensor system for urban tree health monitoring. So let's start from introduction. Trees are an important component of the urban ecosystem. They provide many environmental, economic, and social benefits, including removing air pollutants, cooling the urban environment, and improving human thermal comfort, reducing energy consumption related to air conditioning, adding economic value to urban neighborhoods, and reducing stormwater runoff arising from impervious urban surfaces, etc. LoRaWAN is an open media access control layer protocol for long-range communications and for wide area networks. It is based on LoRa, which is a radio frequency modulation technology derived from chirp spread spectrum technology. LoRa-based devices can operate with ultra-low power and can communicate with the internet-connected gateway wirelessly over a long distance, which is up to 5 kilometers in urban areas and up to 15 kilometers and more in rural areas. Now let's take a look at the system design. The LoRaWAN network here is relatively simple. The Arduino MKR1-1300 development board, which has LoRa connectivity, was selected as a controlling unit of the system. And the Things gateway was used to enable communications between the system and the internet, and the data were collected on the Things network platform. The LoRaWAN sensor system consists of 3 sensors. The Adafruit SHT 30 mesh protected weatherproof temperature humidity sensor was selected to measure air temperature and air humidity. And the Adafruit Stemma I2C capacitive soil moisture sensor was selected to measure soil moisture. To waterproof the Stemma soil moisture sensor, heat shrink tubes and epoxy gels were used. The waterproof one-wire DS18B20 compatible digital temperature sensor from Adafruit were chosen to measure soil temperature. And a circuit board was designed and fabricated to connect the 3 sensors with the Arduino LoRa board as an integrated wireless sensing system. And the system operates at 915 megahertz frequency band, and it is powered by 2 1.5 volt AA batteries. Besides the custom-built LoRaWAN sensor system, a further 2 sensors were employed, which are a precision point dendrometer used to measure radial tree stem or trunk growth. It provides high precision measurements at micrometer level, and a reference soil moisture sensor, which provides 3% accuracy in typical soil conditions. And here is the system diagram. To protect the LoRaWAN sensor system from environmental damages, a plastic container was 3D printed, and all the leads from the sensor elements were coated in waterproof epoxy and made long enough to enable some sensors to be buried in the soil near the monitored tree. So the LoRaWAN system, sensor system and the other sensors were installed on a linden tree located at the lower west side of Columbia University's Morningside campus. All the soil moisture and the temperature sensors were buried in the soil at the foot of the tree with a depth of 15 centimeters. And the air temperature humidity sensor was attached to the tree trunk at a height of about 80 centimeters. The ancillary case of the LoRaWAN sensor system was fixed on the ground close to the tree trunk. The system was programmed to sample and to send data to the Things network every 10 minutes. The point dendrometer was already mounted on the tree trunk at a height of 2.2 meters, and its measurement interval was set to be an hour. The 2 data loggers of the dendrometer and the reference soil moisture sensor were securely hung on the tree trunk using a tree mount strap. The dendrometer data can be downloaded online from the company's website, and for the data from the on-site EC5 soil moisture sensor, it can be downloaded on-site using the designated data cable. So here is the tree that we monitored, and here is the location of our LoRaWAN gateway. It was set up in a top floor apartment on the lower east side of Columbia University's Morningside campus. So before the test, the TTN Mapper app was configured on an iPhone to link the phone's location with the Arduino LoRa board. Thus, the board's location would be recorded while taking measurements. The board was set to send test messages to the gateway periodically. It was held in hand and was moved around the whole campus, which had a sense of about 480 meters by 260 meters. After the measurement, to summarize the collected signal strength data, a mesh grid covering the whole campus was generated in the ArcGIS Pro software. The average RSSI in each grid cell was then calculated. So here are the analysis and results. As shown in the figure here, the Arduino LoRa board was able to transmit data to the gateway throughout the whole campus. The average RSSI in grid cells ranged from -120 to -83 dBm, with the strongest signal at the lower part and weakening signal strength when moving to the upper part. And here are the sensor data. So we did a 9-day test for the system. The stemma capacitive soil moisture sensor was found not to be sensitive enough to soil moisture changes. Thus, the data from the reference soil moisture sensor were used for analysis. In future developments, the stemma sensor will be replaced. So in figure A here, the green line is air humidity measurements, and the blue line shows soil moisture, and the x-axis is date time. So as shown in the figure here, the general observed trend of soil moisture sensor at the base of the tree was a gradual drop. This was because there were only several light rain events, and the rain intensity was not high enough to replenish the soil moisture. And this was partly because the tree's canopy effectively captured light rainfall events. And several high spikes of air humidity were observed almost every morning at around 2 a.m. They were found to be the campus sprinkler system spring water. This was consistent with the soil moisture measurements, as there were several small increments in soil moisture during those periods. And the detection of the sprinkler system proved the system's ability to closely monitor the microclimate around the tree. Usually, such data cannot be obtained from local weather stations. And for air temperature and the soil temperature, let's look at figure B here. So the light blue line is air temperature, and the orange line is soil temperature. We can see diurnal cycles of air temperature were present. The temperature usually reached its highest at around 2 p.m. to 3 p.m. and achieved its lowest at around 2 a.m. to 3 a.m. The low spikes of air temperature, which occurred almost every morning at around 2 a.m., were also found to be associated with the operation of the sprinkler system. It was also shown that the air temperature was highly negatively correlated with the air humidity, with a Pearson's correlation coefficient R equals -0.65, and the p-value was less than 0.0001. And comparing to the air temperature, the soil temperature cycled in a much narrower range, showing the soil's ability to buffer temperature swings. The soil temperature and the air temperature were found to be cross-correlated from the cross-correlation analysis. Comparing to the air temperature, the soil temperature cycled in a much narrower range, showing the soil's ability to buffer temperature swings. The soil temperature and the air temperature were found to be cross-correlated, and from the cross-correlation analysis result, the two variables correlated the most at a time lag of 390 minutes or 6.5 hours, with the Pearson's correlation coefficient R equals 0.33 and p value is smaller than 0.0001. So here, figure C shows the dendrometer readings. The red line here is the radial stem growth of the tree, and the brown line here is the hourly radial stem change. It was showing that the tree was gradually growing at an approximate rate of 20.53 micrometers per day for the tree trunk diameter, and the tree would expand and shrink during a day. A study found that the tree's daily radial increment values were highly and positively correlated with daily ambient humidity, daily ambient temperature, and daily soil temperature. However, since only 9 days of data were collected for our test, longer observations are needed to compare with previously reported results. So instead, we analyzed the tree's hourly radial change and found that it was correlated with air humidity, with R equals 0.21 and the p-value is less than 0.01. In addition, as shown in figure C here, there were several low spikes of the tree's hourly radial change. They all coincided with the operation of the sprinkler system, suggesting that it was possible that the tree would contract significantly almost immediately after being watered by the sprinkler. But this needs to be further investigated with more observations over a longer time period. So here comes the conclusion. A LoRaWAN-based wireless environmental sensing system was developed in this study. It reliably monitored environmental variables around a live urban tree. And because of its wireless capability and the availability of LoRaWAN gateways across the city, this system can be easily scaled up to support an entire network of sensors. And when combined with a point dendrometer, its measurements can help understand the impact of microclimate and other factors to tree health and tree growth. Future works for this project includes implementation onto multiple trees across New York City, integration with other environmental sensors like CO2 sensor, ambient light sensor, testing and improving the power performance, and testing on forest trees in the nearby Lamont Doherty Earth Observatory and the Black Rock Forest Conservatory. So this will show the efficacy of our sensor network across multiple settings. All right, thank you for joining my presentation. And if you have any questions or suggestions, you can reach me at this email address. All right, thank you again. Bye-bye.